Well, guys, here we go. The date today is the 24th. Frighteningly, we are going to have 3 weeks of school before we hit Labor Day. It's bordering on child abuse. But, yeah, Labor Day is actually the latest it can possibly be this year. It's on the 7th because the 1st is a Tuesday. So we're pushing through. But guys, again, today is the 24th. The topic for your notes is data and measurements. Because you all now have notebooks that you can organize, this will, of course, then become your second day of notes in the notes section of your notebook. And then, of course, I just gave you your homework, and you can get that filed away at some point as well. But guys, what I'll always do when we start class is I will give you the big picture. What are we going to do today? And guys, bottom line is this. Starting at the end of the week, we're going to get you guys into lab. And first we're going to get you settled and teach you how to not catch on fire. But once we're done with that, you guys are actually going to be in lab. You're going to be doing experiments, doing reactions, collecting data. Guys, we're going to collect a bunch of data in this class. So what I'm going to do today is I'm going to help you be an intelligent consumer of data. So what we're going to do is we're going to talk about the 2 types of data that we will collect in this class. And then what we're going to do is we're going to focus in on one of those types of data and talk about how good it is. And we're going to talk about that descriptively, and then we're going to talk about that mathematically. So guys, the big picture is this. 2 types of data. We'll talk about both. Make sure you know what you're doing. Then we're going to put one of those data types away, and we're going to look at the other type, and we're going to talk about how good is that data, both descriptively and mathematically, and that's the day. You ready to go? Okay, so guys, here we go. So as promised, 2 types of data, right? And guys, you need to know both of these terms, so I would encourage you to get these in your notes, because starting early next week, I'm going to come to you and I'm going to say, all right, guys, today in this lab, we are going to be collecting a bunch of quantitative data, and we actually are. The first lab that we are going to do is exclusively quantitative, but because you are also budding young English students, you all know that the root word of quantitative is what? Quantity, right? It is an amount. So guys, when we talk about quantitative data, we're talking about data that is derived from measuring or counting. Now guys, here's the trick. If you're measuring or counting something, those numbers then always need to include, or that data always needs to include numbers and units. So when you've got properly recorded and communicated quantitative data, you always measure or count something, and you will always have a number, and that number will always have units. If it doesn't have any of that, it's not right. Now guys, if you've taken physics, you've done this before, because this is what you do in physics. You make a lot of measurements, then you put units on your numbers. This is physics, this is chemistry. This is biology. The other type of data, but we'll be collecting this as well, the other type of data is qualitative data. Now guys, do the same thing. If quantitative means quantity, what does qualitative mean? Quality, right? But when we say quality, we don't mean good or bad. When we say quality, we mean descriptions. What are the qualities of what it is that I'm experiencing or doing? So guys, qualitative is derived from observation, and it's descriptive. Many times it's in sentence or paragraph form, but it doesn't involve measurement. It doesn't involve numbers or units. You're simply describing what you're seeing. So there you have it. You got it? Questions on qualitative and quantitative data? You sure? You can tell the difference? Okay, prove it. So guys, here's what I need you to do. Obviously, don't try to draw this into your notes. Some of you printed the notes and you've already got it in front of you. But guys, it doesn't matter what you're looking at, but actually what you're looking at is a computer-generated model of an enzyme. That's the green mesh. An enzyme attacking a biologic molecule. This is actually a sulfur atom, and the enzyme is actually ripping this molecule apart at that sulfur atom. Doesn't really matter, but that's what the picture is. Guys, here's what I want you to do. In your notes, and please do this because I'm going to call you out and you're going to freeze, so you want to write something down. Guys, in your notes, write down a qualitative and a quantitative observation from this picture. One of each. You said you understood it. I look for questions and you said you ain't got any, which means you should be able to do this. A qualitative observation and a quantitative observation from this picture. A quantitative and a qualitative observation. You okay? So guys, let's talk about it a little bit. So listen to what your classmates say and see whether you agree or not. And then we'll throw you some curveballs down the road. So Josh, forgive me, I'm going to call you out. So give us a qualitative observation from this picture. Say that again. Lovely. So, and it might be the green thing, or I'm not sure what you're referring. Anyway, but he's describing what he's seeing. I mean, not in great detail, which many times is just fine, but he's saying it looks as if this thing is connected to the sulfur atom. He's taking in what he's seeing and he's trying to describe it. So that would certainly be a qualitative observation. So Cooper, let me come to you, and why don't you give us a quantitative observation from this picture? Do you want to phone a friend? How about phone a sister? Go. Sorry, you got stuck. What do you got, Lexi? Quantitative. Perfect. Does that count? 5 white balls? Let's think about the criteria for a quantitative observation. So if it's quantitative, it has to be measured or counted. Did she measure or count something? You bet. Did she have a number? 5, absolutely. Did it have units? 5 white balls. I would say that met the criteria. She counted something, she gave us a number, and she gave the number units. Can we sign off on that? We okay? Do you understand the distinction between the two? Qualitative and quantitative. You okay? Okay, so guys, if you're feeling more comfortable with this, let me give you another opportunity just to make sure. Forgive the Mountain View colors. It's all I could find hurriedly on the internet. So guys, again, qualitative and quantitative observation from this picture. Third, you bet. Qualitative and quantitative observation for this one. One of each. And then I get to do one. Qualitative and quantitative observation. All right, Cooper, you're still in the hot seat. You didn't get to dodge the bullet that easily. Give us a qualitative observation. So qualitative. Perfect. I know we don't like to talk about that here, but I think we could easily look at the football player on the left and we could say that he's dressed in maroon and gold, right? And those are definitely descriptive. It's giving us a sense of what we're seeing. I would say that that's definitely qualitative. You guys okay with qualitative? Jill, give us quantitative. Give us something quantitative from this picture. Perfect. 2 people. It's got a number, it's got units, people, and it's something she measured or counted. Guys, you okay with this? Qualitative, quantitative? So if I come to you and I say, guys, today we're going to do a quantitative lab, you know you're going into lab and you're going to be taking measurements, writing down numbers, and putting units on them. If we're doing a qualitative lab, what's your data going to look like? Sentences. We watched the thing do this and this, and you're just describing what's going on. You good? Okay, so what about this, guys? Ready? We're going to flip the coin a little bit, and I'm going to give you an observation, and you decide if it's quantitative or qualitative, flipping the process. So guys, what if I told you that the football player's jersey has the number 24 on it? Qualitative or quantitative? I'm hearing both. I'm hearing either. Which one is it, gang? Qualitative or quantitative? I'm hearing a little bit of both. Is anybody willing to actually try to justify their response? Qualitative or quantitative? Is it Mason? Go ahead. Okay, but I'm going to argue with you. It's got a number. It always includes a number. I got a number, 24. What's that? But what else don't I have? Go ahead, Abby. Exactly. Guys, and I know that that's where you're getting, and it fails on both, right? But guys, you got to understand that distinction. I gave you a number, but numbers are not always quantitative, and Abby hit it right on the head. It was not derived from measurement or counting. When I said the jersey has the number 24 on it, I didn't measure anything about 24. I'm simply describing what I'm seeing. And because it didn't include measurement or counting, and because, as Mason pointed out, there are no units, it is in fact qualitative and not both. Groovy? All right. So guys, watch your eyes. The lights are coming back. And now here's what we're going to do. Watch my hands. So we just did qualitative and quantitative, right? Qualitative is descriptive. Quantitative is numbers, counting in units. Guys, here's what you're going to do. Mentally, put qualitative in your back pocket. We're done with qualitative for the rest of the day. Now what we're going to do is we are going to look more closely at quantitative. But don't let this throw you, but do put it in your notes. Guys, what we're going to do now is we are going to talk about the quality of quantitative data. And you're going, wait a minute, I thought we put qualitative away. We did. What we're talking about now when we say quality is how good is it? So we're going to talk about how good is the quantitative data that we collect. So guys, the story goes like this, and you're going to be doing things similar to this in a little bit. Say that we want to measure the height of Cooper's table here, and so we get down with this meter stick. Good heavens, this thing's nasty. Anyway, you get down here with this meter stick, and you're making this measurement, and I come back to Cooper, and I say, Cooper, your table is 71.2 centimeters high. And he goes, are you sure? And I say, yeah, I'm sure. I'm sure because I know that my number is very... What are words that we use to describe good measurements? Very precise, very accurate, very exact, very correct. Guys, I can get it for you. There are all these terms that we talk about when we talk about good data. But guys, you got to understand that all these terms don't mean the same thing. Precise and accurate are the two words that we're going to use. But guys, understand they don't mean the same thing. So if you turn to somebody and you say, yeah, Cooper, I'm sure of that number. I know that it's precise. And then if I go to Cooper and I say, I know that that number is accurate, I'm telling him two radically different things, and you've got to understand the difference. So here's what you're going to do. Skip down 7 lines in your notes. Wait, yeah, 7. Skip down 7 lines in your notes, and then draw yourself 3 bullseyes. They don't have to be shaded. You just need big circle, little circle, big circle, little circle, times 3. Okay, so guys, here's what we're going to do. Again, the 2 terms that we're focusing in on are accurate and precise. So watch up here. Here's what I'm going to do. I'm actually going to, first thing we're going to talk about is precision. So go ahead and write down precision here. But then also write it down underneath the leftmost bullseye. So the first thing that we're going to talk about down here is precision. So here's what we're going to do. I'm going to come back this way. And electronically, right? Not really with a gun. But what I'm going to do is I'm going to fire 5 digital shots, if you will, at this target. And these 5 shots are going to have, as you wrote down here, a high level of precision. then what you're going to do is you are going to define precision up here given what these shots look like. So here we go, 5 shots. 1, 2, 3, 4, 5. That is a very precise grouping of shots. You'll notice I never hit the bullseye. Because what does precision mean? Up above in your notes, up here, given what I just did, define precision. What does it mean to be precise? It doesn't have to be big, it just needs to describe what you're seeing. So Lexi, what did you say? What does precision mean? Perfect. In the same spot. Other things you guys wrote down? Throw them out. Y'all wrote down something. What'd you write? Dang it. That's actually the right. Have you taken statistics? Yeah, actually deviation is actually the correct term. So Lexi said, say it again. Sitting the same spot. Mason brought up the word deviation, which is actually the correct term. Guys, I went like this. I just said well grouped. If you're precise, you are very, very well grouped, or maybe another way to think of it is that it's repeatable. That you're doing the same thing over and over and over again in much the same way. But guys, notice the problem. You can be precise and still be wrong. For some of you, this is sort of your life story. You keep doing the same wrong things over and over and over. Just tell your parents you're precise and they'll understand. But guys, really, this is what precision looks like. It just means well grouped. Notice that it doesn't mean correct. If you're shooting for the bullseye, you can be really precise and never hit your target. You get the idea? Do you see the distinction? Okay, so do this then. Guys, we're going to play this game a little bit differently. The next time, I'm going to give you the definition for accuracy. The next thing in your notes, I'm going to give you the definition for accuracy. You're going to fire the shots. You ready? So accuracy means correct. If you are accurate, you are correct. So now what I want you to do in this middle target is label it accuracy and then fire your 5 shots. Draw 5 accurate shots into that center target. And then I'll show you my shots. I don't think you're going to like them. So guys, again, middle target, 5 accurate shots. You ready? You ready to see mine? Guys, tell me what's going on here. You ready? And I actually know that these 5 shots are perfectly accurate. Watch. 1, 2, 3, 4, 5. That's perfect accuracy. And I never hit the bullseye. But wait a minute. I thought we said accurate means correct. How can these be accurate if I never hit? You understand we're shooting for the middle, right? I never even hit the red. And yet those 5 shots have perfect accuracy. How can that be? Can anyone explain it? Keep going. Keep going with that. Josh, tell us what you're thinking. Because you're absolutely right. Oh, where'd my pen go? Oh, man. Does anybody see my pen? Is there another one over here? Somebody. What's up with that? Who would steal? All right, I'll be back. Man, it's gone. Yeah, where's it at? No. Ha! Never mind, we found it. Look, my pen. All right. So, keep going, Josh. Tell us what you're thinking. Distance, what'd you say? Yeah, so guys, do this. Imagine, and I swear to you, I tried to do this and I couldn't get Keynote to do it. But imagine if you could take these 5 points and make them collapse on each other towards the middle. Or maybe think about it this way. If you could go here and here and here and here and here, where would they all meet? Right in the middle. Now guys, here's the deal. What is that process, as Josh is saying, of closing them in? What is that process of closing them in actually a representation of mathematically? An average. Can you see it? If we took these 5 points and if we averaged them out, they would actually land right in the middle on average. So guys, what's the take-home message from that? We will we will seldom do a lab once. When we collect data, we will collect multiple pieces of data and we will average them because averages are always more correct than individual data points. So when we collect data, we will take averages and that will help ensure that we're closing in on the actual value, the accurate or correct value. Get the idea? Okay, so guys, bottom line is this. You can be precise and be wrong. You can't be accurate without taking lots of shots. So what we want to do, and this is what you're going to do now, guys, down underneath this bottom right, or the right one, write both. Our goal here is actually to be both. We want to be accurate and precise. So guys, do that. Why don't you now draw in 5 shots under that right-hand target that are both accurate and precise? What's that look like? Accurate and precise. Now guys, I would offer you this, probably what a lot of you drew. 1, 2, 3, 4, 5, right? Accurate and precise. But I'm guessing that at least one of you drew something that looks radically different from what I did. Anyone? Say it again, Josh. But hold on. So Josh is saying 1 dot, but I told you to draw 5 shots. So what's going on? 5 shots through the same hole. Guys, that's our goal. It really, perfect accuracy and perfect precision looks like 1 dot right in the middle. Right in the middle, and guys, think about this with me. It's a question. What does right in the middle tell us? Accurate or precise? If it's right in the middle, does that tell us accurate or precise? That's accurate, right? Because it's right in the middle. It's hitting exactly where we want to, so that's accurate. But what does it tell us that there's 5 shots through the same hole? Is that accurate or precise? That's precise. And that's, forgive the pun, what we're shooting for. We want to be, that was bad. We want to be accurate and precise. Accurate in that we're right in the middle, and precise in that it's 5 shots through the same hole. So guys, how are we doing? We've got qualitative and quantitative data. Qualitative is descriptive, quantitative is numerical with measurements and units. Then guys, we talked about the quality of quantitative data, and we said that we want our quantitative data to be accurate, which means correct, and also precise, which means repeatable. Good to there? Okay, guys, we've got one more thing to do. The last thing that we need to do is talk about how do we communicate accuracy in measurements. This is how we're going to wrap up the day. We've got about 10 or 15 more minutes, and then you'll have time to work on homework and put your goggles away. So guys, think about the progression of what we're talking about. We started with qualitative and quantitative, then we focused on quantitative, and we said we want our quantitative data to be precise, repeatable, and accurate, correct. Now what we're going to do is we're going to talk about how do we communicate accuracy? How do we tell the world that our quantitative data, our measurements, are accurate, are correct? So how do we communicate the correctness of our measurements? Well guys, in order to show you this, what I'm going to do is I'm actually going to collect with you some quantitative data. Don't try to write any of this down, just watch and you're going to get it. You ready? But guys, at the very end of this, I'm going to do a little play on words with you. Don't miss it, because if you do, you're going to understand this. So here we go. Guys, this is the thing that we are going to measure to collect some quantitative data. We're actually going to measure the length of this yellow rectangle. But in order to make a measurement, what do we need? You need a measurer. You need a device. You need a scale. So guys, this is our scale. I left off the units, but all of our measurements will be in centimeters. So when we make a measurement, what's the first thing we need to do? We've got, ready for this? We've got to get the thing against the scale. Dun, dun, dun. You have no idea how hard that was to do. Okay, so now we've got the thing against the scale. So now we're going to come down here and we're going to make a measurement. So how long is the yellow thing? 10 centimeters, right? But guys, there's something going on here that you're going to be held accountable for the rest of the year. This you do need to write down. When you make a measurement, this is the rule. You ready? It's in blue. You always estimate 1 decimal place past the scale of the scale. The scale of the, let's make that device. The scale of the scale. In the dictionary under redundant, it says see redundant. There we go. Estimate 1 decimal place past the scale of the device. So guys, what on earth does that mean? You ready? Watch my hands. This scale measures in tens, right? 0 tens and 1 10. It measures in tens. So if the scale measures in tens, we have got to estimate 1 decimal place below that, which is the ones place. Okay? If it measures in tens, we estimate to ones. So here's what that means. Is this yellow thing 9 centimeters long? No. Is it 11 centimeters long? No. It's 10. And so because, guys, it's 10, we are going to record this data, you don't need to write this down, as 10 centimeters. You get the idea? Okay, now, we are now going to make a measurement again, but we are going to make a measurement that is more accurate. So if we want to measure this length more accurately, what do we need? A better scale, right? We can do better than this. So let's try this scale. Now, guys, we have a scale that is broken into individual centimeters. So we bring this down, and now we make a measurement again. But guys, check this out. We now know that this is still 10, but watch how this is different. Because, guys, now we are measuring in individual centimeters. So if we are measuring in individual centimeters, we need to estimate 1 decimal place below that, which is what? Tenths of a centimeter. So here's what you do. Mentally, you are going to break this up into tenths. And now you estimate that way, and you say, is this yellow thing 9.9 centimeters long? No. Is it 10.1 centimeters long? No. So this thing is 10 centimeters long, but we looked for tenths and didn't find any. So what are we going to write down to communicate that this yellow thing is not just 10 centimeters long, it's 10 centimeters long, and we know it's not 9.9, and we know it's not 10.1. What do we write? 10.0. Do you get it? What does this 0 tell us? It tells us that we looked for tenths and didn't find any. Are you comfortable with that? Okay, so guys, let's play that game again. Better scale? Now we're broken down into tenths. So guys, if we're broken down into tenths, what will we estimate to? Hundredths, right? So we bring this down, and there we go. And now, guys, my pen's not fine enough to do this, but imagine that we break this down into 10 little pieces. So now we look at this and we say, is this 10.01? No. Is this 9.99? No. It is still 10. But how do we communicate that we looked for hundredths and didn't find any? What are we going to write down? 10.00. Does that sit okay for you? Okay, now guys, don't miss this. You ready? And I'm not trying to trick you. Answer these 2 questions. So guys, we measured that yellow thing 3 different times. We got 3 different pieces of quantitative data, right? Look at those 3 numbers in red and answer this question. Which of these 3 measurements, top, middle, or bottom, which of these 3 measurements is bigger? Which one's bigger? Come on. They're all the same, right? They're all 10. Guys, these zeros right here don't change the value of the number. All of these measurements are exactly the same length. They're 10. You okay with that? So all of these numbers are the same size. So neither one of them is bigger, but try this on for size. Which of these three measurements is better? Which is more accurate? Top, middle, or bottom? Bottom, right? Why is the bottom measurement better? What allowed it to be better? A better scale, right? But now, guys, imagine this. Imagine if you just came along and you didn't see how these measurements were made. You were only given the data. What would tell us in this number that this number is a better, more accurate measurement? How do you know? How do you know that this number is better than either of these two if you didn't see it being made? What communicates that better measurement accuracy? These zeros. Do you see it? Guys, what do these zeros tell you? They're telling us that we looked for tenths and didn't find any. And we looked for hundredths and didn't find any. So guys, these zeros communicate to us that we measured with a good device and just didn't find any tenths or hundredths. Here we didn't find any tenths. We didn't even look for hundredths. Because if we had looked for hundredths and not found any, what should we have done? Put a zero. So guys, these zeros communicate accuracy. So guys, answer this question. Are those zeros important? They're really important. Why are those zeros important? Because they tell us accuracy. So guys, follow this. I would propose to you that those zeros are so important that they're significant. For those of you that have done significant digits before and hated them, guys, I didn't even tell you what we were doing. Because I knew if I said to you, now guys, we're going to learn about significant digits, your minds would have just shut down because you're like, these are boring, I don't understand them, I hate the rules, they make no sense, forget about it. Guys, you now understand significant digits. That's all there is to them. They're not mystical, they're not crazy. Guys, all significant digits do is communicate accuracy. So guys, let's turn on the lights and let's make that a part of your notes. So guys, all that a significant digit is a number that communicates accuracy. Those zeros in those second two measurements are significant because they communicate accuracy. So guys, here's the deal. Some of you are now closing down your brains because he's going, this guy tricked me. He just made me understand significant digits, but that's as far as he's going to go with this because I hate these things. I did them in physics. I hated them. I don't like them. I was sitting there trying to do significant digits, and there were all these weird things flying around up above me that were like these mobiles, and my head was spinning around in circles, and I just didn't like them, and I'm not going to do this. Remember physics? Guys, don't overthink this. It's not that hard. There's only 3 rules for significant. There's actually 4, but the 4th one says nothing else counts. Guys, if you were overwhelmed by significant digits in the past, please just listen. There are only 3 kinds of significant digits. Rule number 1 says this. If it's not a 0, it's significant. That's 1 through 9. So if rule number 1 says 1 through 9 is significant, guess what the next 2 rules talk about? The zeros. And guys, there's only 2 kinds of significant zeros. So if you can keep track of, if it ain't a 0, it counts. That's rule 1. And then if you can keep track of 2 rules that talk about zeros, you now understand significant digits. It's not rocket science. Let me show you how this goes. Guys, write down the rules. You need to be able to identify significant digits. I would just write down rules. You don't need to memorize these. You will never have to write them down. You just have to be able to do it. You ready? Rule number 1. Non-zeros count. That's it. Any digit that's not a 0 communicates accuracy. That's rule number 1. So let me show you some examples. For example, if you have something that weighs 96 grams, how many significant digits? 2, the 9 and the 6. If you've got something like 61.4 meters long, how many significant digits? All three. None of them are zeros. They're all accurate. Okay? But what if you have something like this, 0.52 kilograms? How many significant digits? Well, certainly the 5 and the 2, but we don't know about the 0. So let's talk about zeros, shall we? You ready? Guys, there's only two kinds of significant zeros. The first one is this, and I bolded and underlined the important words, final and after. Final zeros after the decimal. So now you're saying to yourself, what on earth does that mean? This is what that means. Those are the zeros that you just told me you understand are significant based upon what we did with the yellow thing. So guys, final zeros after the decimal have got to meet two criteria. What does it mean to be final? At the end. What does it mean to be after the decimal? It means after the decimal, on the right. So guys, this is a 0 at the end of the number to the right of the decimal. It counts. These are zeros at the end of the number to the right of the decimal. They count. So let me show you some other examples. 4.72 milliliters. How many significant digits? 3. What about 4.720? All 4, because that's the final 0 after the decimal. You get it? Okay. Then guys, what about a number like 82.00000 seconds? How many significant digits? All of them. Do you get the idea that this is telling us that we looked for tenths, hundredths, thousandths, and 10,000ths of a second, and we just didn't find any communicating accuracy? You get the idea? Okay. So guys, those are two types of significant digits. There's only one more. Oh golly. I hate it when it does this. It did this to us last time too, didn't it? I blame you guys. All right, try this. Rule number 3, trap zeros count. So what is a trap zero? Let me show you some examples. 5092 decimeters. What's a decimeter? Doesn't matter. We'll talk about it later. But guys, what is 5092? How many significant digits? All 4. That 0 is significant because it's trapped between the 5 and the 9. So all 4 are significant. What about a number like this? 8.00035. Are those zeros trapped? They are. The decimal place doesn't trap numbers, but the decimal place doesn't break up trapping. So those zeros are trapped between the 8 and the 3, so they're significant. You okay? So guys, finally this. Nothing else counts, you're done. That's it. You don't even really need to write it down. It's a negative rule. Nothing else counts. But let me show you what nothing else looks like. So guys, for example, 7,000. Why are these zeros not significant? Well, certainly they're not trapped. But wait, they're at the end of the number, right? They're final zeros. Why are they not significant? They're not after the decimal point. Guys, what are these zeros doing? All they're doing is making 7 into 7,000. They're making 7 bigger, but they're not saying anything about accuracy. And then similarly this, 0.000758, these zeros are simply placeholders that push that number to the right, but they're not talking about accuracy, they're just talking about small. Significant zeros here would look like this, because then they're telling you you measured the small thing accurately. Do you get the idea? Okay, so early out today, 1:15, you guys get home or go off to practice. Then tonight, family home evening, you're looking for something to do with your family. Allow me to offer this as a suggestion. You ready? You go out here and you go to this website. What could it possibly be? A significant digit number generator, super fun thing of science. You ready? This could be big fun for the whole family. Here we go. New number. Oh no, it's in scientific notation. What are we going to do? Guys, how do you figure out significant digits for numbers in scientific notation? Real easy. You just look here. How many significant digits in 2.69? 3. This is good. You ready? Check your answer. Significant digits, 3. Check answer. It's correct. That's big fun. You ready? How about this? That one's easy. That one's easy. That one's easy. What about that? How many significant digits? 3, right? The zero's trapped. How many, how about that one? How many significant digits there? What about those zeros? Aren't they after the decimal? Yeah, but they're not final, right? And therefore it's only 4. And guys, I suspect you got probably 3 or 4 good hours of family fun just doing this, huh? Okay. But guys, seriously though, in all honesty, if you need to practice on identifying significant digits, it's a good place to go. But whether you choose to do that or not, guys, this is actually the thing that you've got to be able to do with significant digits, and I would encourage you to write this down. You have got to be able to round to significant digits. This is sort of where the proverbial rubber hits the road. So guys, what we're going to do is we're just going to do the top 3. I think that'll be sufficient. And then you'll have time to work on your homework and stow your goggles away. Once again, guys, for those of you that did come in late today, I'm going to give you the benefit of the doubt. Although I know that giving people the benefit of the doubt the second day can quickly turn into, oh, this is just really the way things roll. Don't make that mistake. But guys, we'll go over these top 3, and then you'll have time to work on homework. You're ready to go? So the idea here is the number is given, and then the number of significant digits to round to is in parentheses. So guys, let's do the first 3 together. Looking here in the left-hand upper left, how many significant digits are in this number? 6, right? All of them. So I would encourage you to do this if you're just getting started with these. We need 4 significant digits. So start at the left, and you can even just draw dots above them if you need. Those are the 4 significant digits we need to round to. Now, because none of you asked questions about how to round when we graded homework, that tells me you all know how to round. So now we can go here and we can look at this digit, which is a 2, which tells us to round which way? Up or down? Down. So we're going to go 314.7. Now, do we replace the 2 and the 1 with zeros? No, remember last time we said no. This is why we don't. What if we did replace those with zeros? They're significant. That's why I taught you the rule last time about truncating digits below the decimal, because if you replace them with zeros, they're actually significant zeros. That's why I taught you that last time. So that would be the answer. Let's look at the next one. How many significant digits in this number? Careful. 4 or 7 or 6? It's just 4. These digits are oh golly, that didn't turn out the way I'd hoped. These digits are significant. These zeros are not. They are after the decimal, but they're not final after the decimal, so they don't count. So if we need 2 significant digits, we're just going to go 1 and 2. So we go 0.00. Then the 7 says round up, and we get 1/8. Is that okay? And then guys, finally down here, how many significant digits in this number? Is it 4? Why is that 0 significant? It's trapped. So we've got 4 significant digits. We want 2. So we go 1, 2. The 9 tells us to round up. So we get 81. Now, do we replace these digits with zeros? Yeah, we do, because it's above the decimal. But those are not significant zeros, because they're not below the decimal point. Now guys, one other thing I'd like to mention to you. When you're rounding numbers in scientific notation, just pretend like this isn't here, round that, and then add the exponent to the end. So there you have it. Guys, take a look at the homework and let's talk about how this rolls. The top of this page, you're identifying the number of significant digits. The bottom of this page, you're then taking the numbers from above and rounding them to the number of significant digits requested, just like we did on the board. And then on the back, you've got 4 descriptive things to write towards. And guys, we will grade this on Wednesday. Wednesday will be our last day of numeracy stuff, and then we will get you into lab. So guys, if you'd like to jettison your goggles, go next door. If you already have or don't have them, you need to if you don't have your goggles, make sure you have them here by Friday. And guys, you have the rest of the time to work on your homework. We have about 6 minutes left. Dig in. Sharpies are next door. Go get them.